Hello everyone, welcome to the third lecture of module 5, which is on combinational circuit design. So far, we have looked at how to size these combinational logic gates, these complex logic gates with reference to the minimum sized inverter. We have also seen the delay analysis and what was the assumption in the last lecture. So while calculating the delay, the assumption was that the load capacitance is dominated by the external capacitance and not by the internal capacitance. And then we were sizing the gates so as to make this delay of this combinational logic gates less than or equal to the delay of the inverter. But the assumption was there that CL is entirely dominated by the external capacitances and not the internal capacitances. And you are also looking at these gates in isolation. But as we also discussed for inverters or while designing inverters, that analyzing or designing these gates in isolation, that is purely an academic exercise. In reality, what do you have? In all these digital circuits, you have these gates connected, right? So once these gates are connected, minimizing the propagation delay becomes a fairly tough task. It's not that easy as designing a gate in isolation for minimum propagation delay. So let us look at how can we minimize or optimize the propagation delay when we are talking about a chain of such complex logic gates. Disclaimers remain same. So what we are discussing here is about a chain of complex logic gates and what should be the effective fan out and how should we design this chain of complex logic gates, how do we size them so as to get optimal delay, right? So we have already performed this exercise for chain of inverters, and there also we discussed that minimizing delay of any logic gate in isolation is useless because in reality they are connected. So in all these digital circuits you have these complex logic gates connected in a chain, and we have to look at the overall big picture in order to minimize the delay or for any other thing. We have to look at this chain of logic gates instead of looking at these devices in isolation and assuming that the output capacitance or the load capacitance is kind of dominated by the extrinsic capacitance. There can be some exceptions as well. It can be dominated by the internal capacitance as well, because in chain you do not necessarily have the intrinsic capacitance is lower as compared to the load capacitance. It's not necessary. So let us go ahead and take inspiration from the chain of inverters that we already do. So as I discussed even while discussing inverters, that in this course, if you understand inverters well, you can extend the same principles for designing of complex logic gates as well. So we'll be doing the same thing over here. So let us first discuss or let us first recall what we did for the inverters. So when we were discussing about chain of inverters, we found out that there was this optimal fan out. That was a factor by which we had to upscale each of the inverters in the chain, right? So first inverter, if it is sized as 1, second inverter would be sized F, then F squared, then F cube, and so on. And what was this optimal fan out F? So we found out that this optimal fan out F was equals to capital F raised to power 1 by n, that is nth root of this capital F. And what was this capital F? So capital F was nothing but the electrical effort of the whole chain. So what is that electrical effort of the whole chain? It's simply load capacitance, which was present at the output of the chain, divided by the input gate capacitance of the first inverter in the chain, which was sized as a minimum sized inverter. And what is N here? N was the number of stages, and we could have also found the optimal number of stages by taking the derivatives again of the propagation delay with respect to N. We did all those exercises, and we found out that the optimal F in that case was close to 3.624. Right? So these were the things that we've discussed already when we were discussing about chain of inverters. Now what we'll do in this lecture is we'll extend that concept and then we'll try to find out the optimal fan out of series of complex logic gates, not necessarily inverters. So how do we do that? How do we go about it? So what we do essentially is we first modify the delay equation of the inverter. So the delay equation for inverter came out as TP0 1 plus F by gamma. What was F? F was what? F was basically C external by C internal, right? So the output capacitance of a stage divided by the input gate capacitance. That was your F, or the fan out of your inverter, what we are considering. So what we do is, for extending this equation for chain of complex logic gates, what we do, we modify this equation and we modify it as this. So now if this TP is the propagation delay of a complex logic gate, and this is given by TP0, which is the intrinsic delay of a minimum sized inverter, multiplied by this factor P plus G times F by gamma. So you see two new terms here. One is P, one is this G. We shall discuss what exactly is this P and G. But first, let us discuss what is this TP0. So TP0 is intrinsic delay of the minimum sized inverter, which remains same as the delay of the inverter. Now F here, the meaning of F here also remains the same. F is the effective fan out or electrical effort that is given by external load to any stage divided by the input capacitance of the gate. This also remains same. Now, what are these new terms which have been added? So we have added this P. So what is P? So P is nothing but it denotes the ratio of unloaded or intrinsic delay of complex gate to that of the delay of inverter. Now, so far we were doing that analysis of delay analysis or sizing of that. So while sizing, what we were assuming that the pull-up network or the pull-down network of these complex logic gates, they give the same amount of current as the minimum sized inverter, right? We were looking at the worst case, and then we were trying to size them such that the resistance, effective resistance or the effective current drivability of the pull-up network or the pull-down network was same as that of the minimum sized inverter. But when calculating the delay, we were taking 0.69 R equivalent times CL. And we were saying that this load capacitance is dominated by C external. So we were assuming that there was an external capacitance connected to the output of those logic gates, and that was dominating the entire capacitance, load capacitance. But here, this P factor simply represents the ratio of unloaded or intrinsic delay of the complex gate to that of the inverter. Now, we know that we have made the driving strength or the equivalent resistance equal to that of the minimum size inverter via sizing. So if the R equivalent is same for both, then what can you say about P? Then P, that is the ratio of intrinsic delay of complex gate to that of the inverter, is simply C int of that gate divided by C int of that inverter. So it's basically the intrinsic capacitance of the gate divided by the intrinsic capacitance of the minimum sized inverter. This is how we define this parameter P. And this P into TP0, that determines your intrinsic delay of the complex logic gate. Now let us look at this parameter G. So what is G? G is known as logical effort. So what does that mean? So it simply denotes how much more input capacitance that complex gate presents as load when it is delivering same current as an inverter. So we have already made the driving current same by sizing. So this logical effort simply tells you how much larger is the input capacitance of this complex gate as compared to an inverter. And why it is important? Because when this complex gate would be added as load to some other gate, then it will add to the delay, right? Because then this complex gates, like gate capacitances, will have to be charged. They will contribute to the load capacitance of the previous stage. So this logical effort also adds delay when used as load, and hence it increases the delay, right? So that is why it is very important. Now, other way of stating it is, given each input presents same input capacitance as an inverter, how worse is the complex gate in producing output current? So one way is to say that we have to equalize the current. So for equalizing the current, how much more input capacitance is the complex gate presenting as compared to an inverter when it is being used as a load? Other way of saying it is, let's fix the amount of input capacitance, and then what exactly is the driving capability of this complex gate as compared to the inverter. So they are just dual of each other. I mean, in one case we are fixing the load current and looking at the input capacitance. Like we are equalizing the driving capability and then looking at the input capacitance. And in the second case, we are just equalizing the input capacitance and then we are looking at the driving current. So both represent the same thing, which is called G, and that is known as logical effort. This logical effort is very important when talking about the complex logic. So let us discuss these factors in detail. So first, let us discuss this P, which is called the intrinsic delay factor. And as we discussed that since we have already made the driving strength equal via sizing, so this P is simply C int gate by C int of inverter. So let us look at it. So since P is C gate by C inverter, what is the C int of inverter, minimum sized inverters? It's beta plus 1, right? So here it's beta plus 1 times gamma CG0, right? Let us look at a NAND gate. So what is the C int of NAND? It's beta plus beta, that is 2 beta plus 2 gamma CG0. So what exactly is your C gate by C inverter here? So it's 2 plus 2 beta by 1 plus beta, that is 2, right? So P factor for NAND gate is 2. So intrinsic delay for NAND gate is twice as compared to minimum sized inverter. Now let us take the case of this NOR inverter, NOR gate. So for NOR gate, what exactly is this Cint? So this Cint is 2 gamma CG0 plus 2 beta gamma CG0. So it's basically 2 plus 2 beta gamma CG0, and we have to divide what? 1 plus beta gamma CG0. So here also, what can you understand? That for 2 input NAND or 2 input NOR, this factor P is simply 2 for both cases. If you generalize it, then you'll find out that, for inverter P is 1, because for inverter, your C inverter by C inverter will always be 1. If you talk about n input NAND, for 2 input NAND, it was 2. For 2 input NOR, it was 2. So if you talk about n input NAND or n input NOR, if you generalize it, it will be n. And for n input XOR or XNOR, it would be n into 2 raised to power n minus 1. Please verify this once. Okay, so once we have discussed about that P, that is intrinsic delay factor, let us discuss about this logical effort, which is G, which is of prime importance when we are talking about these complex logic gates. So what did we say about this logical effort? So it's simply the ratio of the gate as a load divided by the inverter as a load. Because we have already sized it so that its driving capability is same for both pulled up network and pulled down network. So now let us look at one input. So this input here, V in, its C is a gate capacitance equals to 1 plus beta CG0, right? Now let us look at input A here. What does input A see? So input A C is 2 CG0 plus beta CG0, right? So what is G for it? So G is simply 2 plus beta divided by 1 plus beta, right? Now let us look at input A for the case of NOR. So for the case of NOR, what you have here? You have CG0 plus 2 beta CG0. 2 beta CG0 plus CG0. So what exactly is G factor for it? It's 2 beta plus 1 divided by 1 plus beta. So typically, as I told, that beta is equals to 2. So for n equals to 1, for inverter, it's already 1. For n equals to 2, for n input NAND, what is it? It's 4 by 3. 2 plus 2, 4 by 1 plus beta, that is 3. For n input NOR, it's, so for 2 input NOR, it's 2 beta plus 1 by 3, but that is 5 by 3, right? Similarly, you can do it for n equals to 3, and you can also generalize it for n, right? This XOR or XNOR, the logical effort of XOR or XNOR, this is something which is tricky. You analyze it once, and then I'll be discussing about it in the tutorial session, because this 4 comes out assuming that both A and A bar are coming from the same source. I mean, I'll discuss that. But you first try to convince yourself whether for n equals to 2 you are getting 4 or not. And if you're not getting 4, what are you getting? And what is the logic behind that? And please let me know in the tutorial session what you are getting when you are calculating it. And then I'll explain why exactly I've written 4 and what is the correct value. Okay? So you may get 2 as well. I mean, that's totally dependent upon you. That simply assumes whether you are talking about both complement and its true version, like whether you are taking the true version and its complement together, or you are taking them in a separate fashion. That depends upon you. But please do it yourself. I mean, do it yourself. Convince yourself whether it's 4 or 2 or whatever you are getting. And then in a tutorial, let us discuss this, because it's an interesting thing to look at. Okay, so now that we know about this logical effort as well, let us now look at how exactly this normalized delay looks for complex gates. So if you plot the normalized delay as a function of fan out, you'll find out that it has got 2 components. So that follows a straight line. I mean, it's a linear variation with respect to the number of fan out. So here the slopes are different, the intercepts are different, right? But it's a linear relationship with respect to the number of fan outs. So basically, the delay consists of 2 components. One is the intrinsic delay, which should be present even when it's unloaded. And second is the effort delay. Effort delay because the gate is doing some effort in driving other gates. So there are 2 components to this delay, even for complex gates. One is the intrinsic delay, one is the effort delay. Now, this intercept here on the y-axis, that gives you intrinsic delay, right? And the slope, that gives you what? That gives you the logical effort, G. So if you have been given any curve like this, where you have been given a normalized delay as a function of fan out, then just by looking at this curve, you can find out its intrinsic delay factor, P, and its slope that gives you logical effort. Now, how can we change the delay? One effective way is change the number of fan out, you change the delay, right? So you change the effective fan out, you can modulate the delay. Now, this fan out, that is electrical effort, and the logical effort, they are contributing to the delay in somewhat similar manner, right? So what people did is they combined them and called it a parameter which is known as gate effort, H. So this F into G is something which is called the gate effort. They combined both and they named it gate effort, that is F into G, and this made our life so simple. We'll look at it why. So now the problem at hand is we have to minimize the delay for chain of gates, right? And we saw that we can call the delay of individual gates as TPJ is equals to TP0 E plus GJ into FJ by gamma. Now this GJ into FJ, we call this as H of J, right? The gate effort of jth stage. Now the total delay is what? Total delay of this chain of gates would be summation of the individual delay of individual delays. So it will be simply summation j equals to 1 to n TPJ. And if you do that, it comes out as TP0 summation over j equals to 1 to n E plus GJFJ divided by gamma. Now, what are design variables, or what is something which is in our hands? See, GJ is something which depends upon the gate, it's constant. E is something which depends upon the gate, it's constant. So what is in our hand? So design variables are these Fj, that is the electrical fan out of the individual stages, as well as the number of stages. You see how similar this is to the inverter case, the chain of inverter case. There what we did, we first took a particular n, and then we found out the condition for minimum TP, and from there we got optimal value of Fj. So here also we'll do the same thing. So here what we'll do is, for a given value of n, we'll find out first the condition for minimum TP, that is we'll take n minus 1 partial derivatives and then equate them to 0. And once we do that here, what we found out there was that individual, the fan out of the gate should be same. Fan out of the each stage should be same, right? That is what was the conclusion for inverters, chain of inverters. Here what we get as conclusion? Here we get as a conclusion that this logical effort, this H, that is GJ into FJ, that will be same for each stage. So F1G1 is equals to F2G2 is equals to FNGN, and that is equals to H. Where what is H? H is the optimal gate effort. So the conclusion there was that in the case of chain of inverters, the conclusion was that each of the stages should have the same fan out. Here, the conclusion that we get after this is exercise of taking partial derivatives, we get the conclusion that each stage should bear the same gate effort. Okay, so that's the difference. So here each stage should bear the same gate effort. In chain of inverters, each stage should bear the same fan out. Look at this difference, and you see how we can extend that analysis to get conclusions here, right? Now, we try to compound these logical effort or gate effort along the path. I mean, there would be a signal path or the critical path through which the signal would be flowing across different stages, right? Now we will try to compound it. Now let us see how we can compound it when we have a chain of stages. So first, let us look at the logical effort. So the logical effort along a path in a network that compounds as path logical effort G is equals to product of all the GJ. So this capital G is nothing but product of all the G's of individual stages. That is how you compound this logical effort along the path, and you name it as path logical effort. And you also define something which is called path effective fan out, which is the effective load capacitance present at the output of this chain divided by the gate capacitance of the first gate, which is in your chain. Now you remember we related this optimal fan out F to this capital F in the case of CMOS inverters, chain of CMOS inverters. Now similarly, similar to the inverter chain, here also we would like to relate this F to the effective fan out F, effective fan out of each stage. However, there is a difference between the two. In a chain of inverters, you had similar gates, and effectively branching was not affecting it much. But here, since these complex gates can have multiple inputs and due to multiple fan outs as well, we can have branching in the path. So because of these multiple inputs and number of fan outs, we can have branching. So whenever you have branching in the path, what happens? Some drive current is directed along the path and some is also directed to the branches, right? So if you have a situation like this, some amount of current, let's say this is your path, critical path, which is under consideration, and this is the branch path. So some current will flow in this path, some will also be directed towards this branch, right? So to take these cases into account, what we do is we also define something which is called branching effort. So this branching effort B is simply defined as C on path plus C off path divided by C on path. So here, what is your C on path? C on path is simply the gate capacitance of this inverter. What is your C off path? C off path is simply the gate capacitance of this inverter. So what exactly is your B? B is 2, right? If we consider that these are identical. So this B is 2. Now, what exactly, why do we calculate this? So the thing is, the effective capacitance over here is 2 times the capacitance of this input gate capacitance of this inverter. However, in this path, along this path, what is the effective capacitance that this load should see? It should see this by 2. I mean, ideally, when this branch was not there, the effective capacitance that this would have seen would have been only the input gate capacitance of this inverter along the path. But now it is seeing 2 times that. So this branching factor or this branching effort kind of increases the effective load that this has to drive. And that is why we take this into account, right? Even this branching effort, this also compounds as product when we go along the path. So this path branching effort, which is denoted by capital B, is nothing but product of all these BJs along the critical path or along the signal path. Now, how can we relate this capital F to this small f? So here, this capital F can be related to this small f by this expression. So this capital F, which is the path effective fan out, is nothing but the product of Fj divided by Bj. So you are simply considering only those fan outs which are contributing, which would have contributed in absence of branching factors, right? So this is how you are doing it. So this capital F, which is the path effective fan out, is nothing but it's the product of Fj, which is the fan out of individual stage, divided by Bj, which is the path, which is basically the branching effort of individual stage, right? So this is how you can relate this capital F to this small f here in the case of chain of complex gates. Now let us find out the optimal delay, or let us find out the optimized gate effort per stage and then find out the optimal delay for this chain of complex logic gate. So for this, we also define something which is called total path effort. So this total path effort is nothing but capital H, and it's denoted by product of this Hj, which is product of the gate efforts of individual stages. And how can you define that? This product of Hj is simply product of Fj Gj, right? That is how you can define it. Now, the gate effort that minimizes path delay is H raised to power 1 by n. How do you get that? See, this H is equals to pi of this Hj, and we saw that for each of those stages, this H is same, right? The gate effort has to be same for minimal delay. So what is this H? This H is nothing but Hj raised to power n. So what is that H optimal? So this H optimal or the optimal gate effort is nothing but capital H raised to power 1 by n. Now, how can you find out the optimal fan out of each stage? So optimal fan out of each stage is simply Fijj is equals to H opt. So Fj is simply H opt by Gj. Now Gj is something that depends upon the type of gate, right? That logical effort depends upon the type of gate and the number of inputs. So you can easily know this Gj. So once you know the Gj, once you know the H optimal, you can easily find out the optimal fan out of each stage, right? And then how can you find out the optimal path delay? Optimal path delay is nothing but it's n times p. So here you see it's sum of all the delays of the individual stages. So it's pp0 n times p plus n times gj fj by gamma. Why n times this? Because this is constant for all. I mean, this has to remain same for all the stages. Now gj fj is simply h, and h is what? H raised to power 1 by n. Hence this expression, right? So the optimal delay is n times p plus n h raised to power 1 by n, nth root of this capital H divided by gamma. Now again the question arises similar to the inverter chain. What is the optimal number of stages, right? So as we did there, We took the derivative with respect to n of this optimal path delay. Here also we'll do the same and equate it to 0. So if you take the the partial derivative with respect to n and equate it to 0, and if you substitute h optimal is equals to h raised to 1 by n, you get h is equals to exponential 1 plus p by h. So this is something that you get, and from here, if you substitute it back, you can get the value of n. Okay. Now, what exactly is this logical effort method? So how you can find out the effective fan out using logical effort method? So let us discuss that. So what you do here, first, you compute the path effort h, capital H. And what is your capital H? Capital H is nothing but G times V times F. How so? So it's simply I times J equals to 1 to n Fj Gj. Now you can do it by Fj Gj by Bj into Bj, right? That is what you can do. Then Fj by Bj, that becomes capital F, Gj becomes capital G, and Bj here becomes capital B in terms of product. So once you do that, you find out that this capital H is nothing but capital G, capital B into capital F. F is easy to calculate. B is also something that you can calculate easily. G is also something that is calculatable. I mean, you can calculate easily. Now, once we have found out this capital H, how can we find the best number of stages? So if you take logarithm here, so H optimal raised to power n is equals to H. So n log of H optimal is equals to log of capital H, right? And we found out that this H optimal is close to 3.5, 3.6 to 4, even in the case of, when we are doing this exercise for this complex logic gate. So n is simply log of capital H divided by log of H optimal. And this H optimal is found out as 3.6 to 4. So it's close to log 4 H. Now then what we can do? We can compute the stage effort H, stage gate effort H as capital H raised to power 1 by n. So first we find out this H, then we find out this n as simply log base 4, log base 4 H. And then how do we calculate the stage gate effort? We calculate the stage gate effort as small h is equals to h raised to power 1 by n. Once we know the gate effort of the individual stages, then we just sketch the path with these number of stages, and then we work from either end. I mean, we can start with the first stage, or we can start with even the last stage, because typically we know the CL or the input capacitance of the first gate. So once we do that, once we know that, then we can find out this C in as simply G times C out by F. So it's pretty simple to calculate. You can calculate, the optimal F as well, and you can find out how to size this different complex gates in a chip.